let's have a conversation today. Yesterday we were talking about the idea of the flow of charged particles. So today I want to. I have two or three goals. The first goal is to apply the idea of Kirchhoff's laws to current flow. The second idea is to develop a reasonable way to deal with systems of resistors, and then hopefully by the end have had an opportunity to practice one or two stepwise reduction questions, but using resistor circuits instead of capacitor circuits. So based on something we talked about yesterday, I do want to at least throw this out there. There was current flowing through all the circuits that we dealt with when it came to capacitors. It didn't take long because the capacitors charged very fast. But even standard copper wires have a certain amount of resistance. Their resistance isn't zero. When we draw a circuit, one of the things that we are kind of saying to the person who's looking at it is that the resistance of the wires is negligible compared to the resistance of the other elements within the circuit. So if we have two resistors, R1 and R2, in a circuit, they have within them the resistance of the wires, or that's somewhat included inside the wires. And it's not because the wires themselves don't have resistance. It's just that if you remember from the capacitor lab, there's a certain amount of tolerance within the resistance, within the capacitance. You guys remember that they might have said there were 50 microfarads on the package, but they didn't test 50 microfarads. What's hard to know is whether your testing device was the problem there, or whether the capacitor was the problem there. But if you look closely at the packaging, it told you that there was a tolerance of probably plus or minus 10%. Resistors are going to have a similar kind of range in that they mass produce these items. And so when they are produced, they are not perfectly the resistance that you want. Your wires will have very, very low resistance compared to the circuit elements, but you can kind of wrap up their resistance within the tolerance of the resistors that you have. We are going to treat, for the first couple of days, we're going to treat our circuits as if they are ideal circuits, which means we have an ideal power supply or an ideal voltage source, and we have ideal resistors. However, when I define what a resistor is outside of the context of the flow of charged particles, resistors are going to be defined in a somewhat circular way, and that's going to be bothersome for you guys. You see, resistors obey what's called Ohm's law. And Ohm's law applies to ohmic devices. So it's again, circular logic, but Ohm's law applies to ohmic devices. What's an ohmic device? Something that obeys Ohm's law. So it's not particularly a great definition, but when we say something that obeys Ohm's law, it means if you apply a potential difference to the device and you measure the flow of charged particles it produces, a device that obeys Ohm's law will have a ratio of the current produced proportional to the potential difference applied and inversely proportional to the resistance in the circuit. Now, this is what Ohm's law looks like. It's not how it's generally written in your textbook, and there's a reason for that, but I'll come to that in a minute. First, you're going to love the fact that we use a capital I for current. So that's the symbol we will use for current. And I don't know why I was chosen. However, for this year and for most of what remains when it comes to circuit design and circuit discussions, I will use a capital I for systems that have a constant current, and I'll use a lowercase I for systems that have a time fluctuating current. Okay? So a capital I for systems that have a constant current, and a lowercase I for systems that have a time fluctuating current. Now, although you may be able to kind of put together what you think the units of current are, don't do it based on this equation. I put this equation out there, but your textbook would write this equation like this. And most textbooks would as well, that Ohm's law is V equals IR. There's a problem with that particular relationship, and I want to be very clear about it. A voltage potential difference can exist apart from a circuit. I mean, I can have a battery just sitting on a table. It is a potential difference. The potential difference exists apart from the circuit. I can have a resistor that's not in a circuit. It's just some conducting piece of material that has some resistance to the flow of charged particles. I can have it apart from the circuit. It retains whatever amount of resistance it is. Most resistors, by the way, are made from carbon or just the same kind of pulverized pencil lead that you guys have right now, but it's packed into a small plastic container with an electrode on either side. So that's what most resistors are, just bits of carbon. They have enough conducting ability to pass current through them, but they have a lot of resistance and they're cheap. So when we make resistors, usually that's all you're going to see is a package that looks like a little capsule with two wires coming out. Inside the capsule, if you break it open, is just carbon. And it's nice and cheap. And if you want to make more resistance, well, we'll talk about the structure of resistors over the next couple of days. But longer resistors have more resistance. That's what it comes down to. So, but they don't usually adjust what's inside there. They just use carbon because it's cheap and it's easy and it's plentiful. Now, that being said, this equation suggests that the voltage depends on the current. And that's not true. The voltage depends on whatever potential difference source you have. It's fixed by the potential difference you're using. So the potential difference already exists. And the resistance is something that you can choose. In fact, you can buy resistors that have a dial on them where you can select how much resistance there is. It's called a potentiometer. And we'll actually use a few of those later in the year. However, current doesn't exist until you have a complete pathway from one side of the potential difference to the other. Current is instantiated, meaning it exists in the instant. So there is no current in this circuit until the switch is thrown. When the switch is thrown and I have a complete pathway from one side of the potential difference to the other, current is created. And the amount of current created is dependent upon the potential difference and the resistance. So I write it this way because it has the appropriate dependence, with current being dependent upon the potential difference. And when I put R here, I probably should put equivalent resistance, but I'm leaving it like this, and I think you'll see why in just a few moments. So this is Ohm's law. Now, most devices are not ohmic. Resistors are ohmic, but most devices aren't. There's tons of different kinds of circuit elements that can be applied to a circuit, and most of them don't obey Ohm's law. So ohmic devices do. And generally, ohmic devices are some kind of conductor that has some standard resistance. They're not special, and there's nothing particularly special about resistors. But things like diodes or LEDs, they don't obey Ohm's law. Transistors don't obey Ohm's law. These are other types of circuit elements, and they have their own rules. A capacitor doesn't obey Ohm's law. We already know a little bit about that. A capacitor does not pass any current. So there is no current passing through the capacitor. There might be current around a capacitor as it gets charged, but when we talk about a resistor, the charged particles are passing through the resistor. So the electrons will pass through a resistor in a way they won't pass through a capacitor. Now, that being stated, current is measured in amps or amperes. But I'll never say amperes, I'll say amps. And an amp is a coulomb per second. And truthfully, the unit of the amp came first. Coulomb came afterwards. But amp and volt were both units that were measured before we understood what was happening inside circuits. Now that we do understand more of what's happening inside circuits, we understand that there's a flow of charged particles, and we understand what those particles are. But for this conversation, amps is a coulomb per second, and it is the flow of charged particles. Now, that leaves us with trying to understand what resistance might be. I'm going to reshuffle this, and when I do, we get a relationship that looks like this. I've just solved this for R. This is to help us understand a little bit about what resistors might be. The unit of the resistor is the volt per amp. you guys are smart cookies, and you know that a volt is a joule per coulomb, and an amp is a coulomb per second, and a joule is a kilogram meter squared per second squared. This is all divided by coulombs, divided by coulomb per second. We seeing all this? Coulomb per second. So I think I can multiply top and bottom of this fraction by seconds, which will give me kilogram meter squared per second cubed, divided by, drop that other coulomb down there, coulomb squared. And now, if I was to write this in a more clear package, I'd get kilograms meter squared per coulomb squared seconds cubed. I mean, that's not pleasant, but that's what we got. Actually, no, it's not seconds cubed. It's just seconds. Thank you. Not seconds cubed, just seconds. It's hideous. So we call this the ohm. That will be the unit of resistance, is the ohm. We'll never break it out like this ever. It'll never show up. But this part you'll have to get used to. Ohm isn't written out like this. Ohm has a symbol that is used, and it is the Greek letter omega is the symbol for the ohm. So if you wanted to write a 100 ohm resistor, you'd write 100 with the little Greek letter omega, and that means 100 ohms. So figured you'd like all that. That's going to be fun times. All right. Ohm's law. So let's clean up our circuit. You'll remember I talked about Kirchhoff's laws, and that there are two of them. There's the one that's based on conservation of energy, and one that's based on conservation of charge. And it says in any loop drawn through a circuit, the sum of the voltage drops will be equal to 0. And the second one says in any junction in a circuit, the charge that flows into that junction has to equal the charge that flows out of that junction. No junctions in this circuit. So to study this circuit, we could use a single loop through the circuit. My goal right now is to develop what equivalency means for resistors. Okay? Just like we did last time. So we're going to take a look at what equivalency would mean for a resistor circuit. Since there's only one loop through the circuit, I'll have a positive voltage because I'm going from the bottom plate to the top plate of my EMF. I will then have a voltage drop across resistor 1, and I'll have a voltage drop across resistor 2, and that has to equal 0. Now, there is only one loop through this circuit, so the junction rule tells me that the current that passes through resistor 1 and the current that passes through resistor 2 have to be the same. Since there's no junction, there's no other places for the charges to go. So current in equaling current out means the current into resistor 1 has to equal the current into resistor 2. That's important because I'm going to use Ohm's law, V equals IR, in that form and sub it in to get IR1 minus IR2. And this still equals 0. Good so far? All right. Again, I'm trying to get an equivalency, so I'm going to move IR for each of these to the other side and get my EMF equals IR1 plus IR2. And then I'll factor out the I and then divide it on both sides. I'm doing that because what I'm going to get on the left side is an expression of Ohm's law. You see it, right? But this is the amount of current that is produced by my potential difference based on the total resistance of the circuit. So this actually equals the equivalency of the circuit. Just Ohm's law again, this time dividing the I on both sides. So resistors in series simply get added together to get the equivalent resistance. You understand that that's the opposite of the capacitor, right? So our equivalency for series we all heard that, right? That was a shared experience? Okay. All right, so generalized expression for resistors in series. All good so far? We sure? Ready to go on? You guys good back there? Okay. Because what do you think we should do next? We should do parallel. Yeah, we should do parallel. So let's take a look at a parallel circuit. Now, this shouldn't be a surprise. I mean, I kind of said to you already that resistors are going to be the opposite of capacitors. So that's still true. But let's still walk it through. Now, if we want to analyze this circuit, can we agree that we'll have to have two different loops to evaluate this circuit and accommodate all of the resistors in the circuit? I think that there are three possible loops we could choose to do. That's one of them. That's another one. And that's a third. I'm probably only going to use the red loop and the blue loop. And the reason is because I think when I look at resistor 1, I have a pretty solid idea that the current is probably going this way through resistor 1. And if I look at resistor 2, I have a pretty good idea that current is going this way through resistor 2. So my current loops are going, for red and blue, go in the direction of the current for both of my resistors. If I use the green one, you'll notice that my current loop goes against the current in one direction and with the current in the other. This next statement is incredibly important, and I would hope you'll listen very closely. When we talk about the sum of the voltage drops in Kirchhoff's law, voltage is negative when you go with the current and is positive if you go against the current. Because it's an increase in potential when you go against the current and a decrease of potential when you go with the current. So when applying Kirchhoff's laws, we have to be mindful. We had a similar issue with capacitors. When we went to the negative plate to the positive plate of a capacitor, it's an increase in potential. When you go from the positive plate to the negative plate of a capacitor, it's a decrease in potential. So for current and resistors, when you're going against the current, it's an increase in potential, and when you go with the current, it's a decrease in potential. And sometimes you don't know what the direction of the current is. I mean, these are real easy, but I can show you circuits in which you might not know the direction of the current, and you will have to pick a direction that you think it's going and stick with it. If you find out by doing the work that the current is negative, it means you picked the wrong direction. But we'll see some circuits like that in the future. So let's take a look at that blue loop first. I'll have EMF minus voltage over resistor 2 equals 0. And then the red loop, I'll have EMF minus the voltage over resistor 1 equals 0. And although I'm not going to use it, we do generate the voltage over resistor 1 minus the voltage over resistor 2, and that also equals 0. Now, if we wanted to use it, it would simplify our work. Because if you're paying very close attention, what it tells us is that voltage 1 equals voltage 2. It's not a surprise. We have a parallel element, and both of those are connected directly to our EMF. So there really is no surprise there. That doesn't change the fact that my first loop should look like that, and my second loop should look like this. That all good for you guys? Of course, it also tells us, that these two, since they're equal to the EMF, they are equal to each other. Now, the junction rule is going to help here. And so here's where I think we'll bring the junction rule in. There is a current going into this junction, which I'll say is I total. And it splits. And on one side, I'll have I1. And on the other side, I'll have I2. Based on Kirchhoff's laws, the current into the junction has to equal the current out of the junction. Is that all okay with you guys? So what I'm going to do is real simple. I'm going to say over here that I1 equals the EMF over R1, and I2 equals the EMF over R2. Is that good for you guys? I'm going to sub that in here and say that this is the EMF over R1 plus the EMF over R2. I'm also going to state very clearly that Ohm's law suggests that from the standpoint of my potential difference, the current produced is going to be based on whatever the equivalency of the resistance is. So by doing a little substitution and a little bit of algebra, I can rewrite the total current in terms of the EMF and my equivalent resistance. Not a surprise here, all the EMFs are the same, so I get 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. All good so far? Not a surprising result, so I guess we could write this as 1 over R equivalents equals the summation of 1 over Ri from I equals 1 to n. This would be for parallel systems. Okay? So, kind of have a standard now. For resistors in series, it's the simple sum of the resistances. And for resistors in parallel, it is the sum of the inverses inverted. We all good? Got a plan? All right. And I'll remind you, Ohm's law. Now, I'm going to state without proof one more thing. Resistors don't contain energy. So talking about the energy storage of a resistor is not a real thing. Resistors consume power. And part of this is because we know that capacitors stored energy because they reached a steady state condition where they had a finite amount of charge inside of them. But we have current that is passing through resistors. So although I will develop this idea formally tomorrow, I am going to state without proof that power dissipated is one of the things we measure for resistors. Their power dissipation, the rate at which they consume energy. And if you don't remember what power is work over time. And for us, there's a couple of other ways to state this. I'll just leave it like that for today. And tomorrow, I'll do a brief review of power and work just for everybody in the room to have that. And then we'll derive what I'm about to tell you. And that is, in a circuit, power dissipation is voltage times current. And obviously, knowing Ohm's law exists, we also get I squared times R and V squared over R as equivalent ways of calculating the power dissipation. Just like the energy storage in the capacitor had 3 different ways we could calculate the energy storage, we have 3 different ways we can calculate the power dissipation. Oh, and what I was going to write here, this is a joule per second, which is also known as a watt. All right. Solving a circuit for resistors is going to be a lot like solving a circuit for capacitors. You're expected to be able to figure out the potential difference across each resistor and the current passing through the resistor, and ultimately be able to determine the power dissipated by the circuit. Ready to do a practice? I don't think I have to start with something super simple this time, because you guys have done a few capacitor circuits, and these are going to be similar. So let's do one at least enough to warrant a couple of steps. And for this one, I will lay it out clearly. All right. Fairly straightforward, kind of benign question. Is this good for you guys? We're going to do stepwise reduction here. And if you'll remember, the idea of stepwise reduction is that we find elements of our circuit that are clearly series and clearly parallel. And we use the rules for series and parallel to reduce the circuit. So I'll start. I like to start by kind of painting a road map, and I'm really only going to draw the resistor portion of the circuit. So I think I see a series element. Do you guys see a series element? So I think my first reduction will be to reduce the series element. But I think at the same time, I see a clear parallel element. Do you see that as well? So I think I'm going to do both reductions at the same time. And this will be my first stage of my reduction. And then this will be easy because those are just in series. So I will be able to reduce that last set by just applying the rules of series. And so this will end up being my equivalent circuit here in 2 steps. So stepwise reduction starts by reducing the circuit. So let's do the reduction. My 2 that are in series, that's just going to be 6 plus 4, so 10 ohms. My 2 that are in parallel, that's going to be 1/6 plus 1/3, and then I have to invert that. So that's going to work out to be, I think, 2 ohms, right? 1/6 plus 2/6 will be 3/6, and then inverted, I'll get 2. So 2 ohms. Are you okay with I don't do all my little basic math? All right. So that's my first step of my reduction. And then my next step of my reduction will be just to add these 2 together, giving me a total of 12 ohms. Look good to you guys? All right. Now that we have this, we can use Ohm's law to figure out the current passing through the circuit. And I have 24 volts and 12 ohms, so that suggests 2 amps of current. V equals IR. Is this too fast? Or is this a nice even pace? Pretty straightforward? All right. So again, this is one of those things where we work backwards. And I want to remind you about Ohm's law. I'm sorry, not Ohm's law. Kirchhoff's rules here. When working backwards, those rules tell us how we take what we just found and apply it to the next step. When we're going back to the next step, I don't think the voltage is going to be the same here. I think the voltage is going to be divided between these two resistors, but there's no junction when we go back to this step. So when I step back to an element and it's in series, series elements have the same current in the same way that series capacitors had the same charge. So these two elements are in series, they will both get the same current. Again, when you step back to a series element, series elements have the same current passing through them. So I apply the current to both. Now, using Ohm's law, I can figure out the voltage across each of these. V equals IR, so 2 times 2 is 4 volts. 2 times 10, 20 volts. Again, I can check my work. 24 total volts. I had 24 before. Looks about right. All good, folks? Any questions here? All right. So we'll step back again. And we're going to be splitting both of these up. Let's start with the top one. I'm going back to another series element. What gets applied to those two resistors that are in series? The current. So I'll grab my current, 2 amps, and I'll apply my 2 amps here and my 2 amps here. 2 times 6 is 12 volts. 2 times 4 is 8 volts. 8 volts and 12 volts is 20 volts. Feel confident there? All good so far? All right, I'm going to take that other one. I'm going back to a parallel element. Parallel elements do not have the same current, they have the same voltage. So I have 4 volts of voltage here. I will apply 4 volts here and 4 volts here. To get the current, it's voltage divided by resistance. So I'll have 4/3 amps and 2/3 amps. I'm going to check my work. I should have a total of 2 amps of current. 2/3 and 4/3 is 6/3. That's 2 amps of current. Now, we have successfully solved the circuit. However, I'm going to have you do this. The power dissipated by this circuit, voltage times current, 2 times 24, 48 watts. Take a moment. There are 4 resistors. Find the power for each of those resistors. You have everything you need to do so, but it better add up to 48 watts. 2 times 12 here, that's going to be 24 watts. 2 times 8 here, 16 watts. 4 times 2/3 is 8/3 watts. And 4 times 4/3 is 16/3 watts. 16/3 and 8/3 is 24/3. 24 divided by 3 is 8. So that's 8 watts there, plus 16 watts, plus 24 watts. 48. I'm not saying it's a way to check your work. I'm saying this has to work this way. Whatever the total amount of power dissipation is on all of those capacitors has to be the power that the equivalent resistor has to be what the equivalent resistor would do. So it has to work out this way. Now, I have no intention of doing a bunch of these in front of you. I think all I can do is sit here and make them more and more complicated, but it's always going to come down to this kind of stepwise reduction. You have plenty of practice in your homework, but I do want to do a couple of things that I think are important. First, I've been kind enough so far this year that with every single circuit element you've seen, it's one that you have a very little difficulty dealing with. So take a look at this circuit. And I'm not going to spend a lot of time doing this circuit. I just want you to look at it. Would you have any difficulty reducing the circuit? Do you realize how to reduce it? Would probably do the series first and then do the parallel? Okay, so yeah.
Is there a problem with doing maybe the parallel first then the series?
Yeah, there is. Because to do the parallel, you would have to know what this whole resistance is first. Does that make sense? Now, if I put this wire in here, does that change what you're going to do? Do you know what I've done to the circuit by just putting that wire there? Do you know what is now in parallel and what's in series? Okay. If you don't, I'm not trying to trick you. You should work it out. But it would be no different than that. Right? That one wire does what this is also doing. Do you guys see that okay? Now, this one you could do as well, right? You do the parallel elements first, and then those would be in series, and you would reduce that afterwards. However, can you reduce this one? Look closely at it. Can you figure out what's in parallel and what's in series? So when I had the circuits before, those two circuits that you saw, there was a clear pathway for parallel and series. There is no such clear pathway here. This can't be reduced by stepwise reduction. So far, all the circuits you've seen have all been able to be reduced by stepwise reduction because they've had clear series and parallel elements. But that's not what most circuits are going to look like. Now, in this class, they're not going to try and throw at you something like this, but the only way to solve this is by applying Kirchhoff's rules or some modification of Kirchhoff's rules and generate relationships. Now, I want you to look closely at this. The number of equations you would generate is actually pretty high. Every junction generates its own set of current equations. Every loop generates its own set of voltage equations. And then, of course, you have V equals IR. So if you look at this particular circuit, it's challenging because you're probably going to generate a system of, I think, 6 to 8 equations that will then have to be reduced using the rules of systems of equations. Now, we don't do circuits like this. And this actually has a name. It's called a Wheatstone bridge. And I don't know how to spell it, but I'll say Wheatstone bridge. It actually has a use. It's for actually figuring out very sensitive resistances. Because there's a potential difference between these two sides, you can tune one of these resistors to reduce that potential difference down. And when you do, you can get highly accurate measurements for resistance. That's what a Wheatstone bridge is used for. But I just want you to be clear, there are circuits that don't have series and parallel, but we stick with the basics.